working just the PowerPoint, right? Yep. Okay. Looks like it's working. All right. So what we'll start is chapter 0. This is the analytical process. And this is really kind of like a setting of definitions for this book. One of the things you're really going to notice about analytical chemistry is that the definitions are incredibly important, because how you define your system determines your very limits of accuracy, okay, your limits of detection, almost everything about what you're going to get out of this, okay? So for example, let's say that you defined your limitation on measurement as being the size of a textbook. Can you measure those distances fairly well? Yeah, you can just go get a ruler, right? And you can do pretty good, and then you could do a machine, and that's not too big. I can do that, and I could use the brand new instrument they just made for $100 million and get it down to smaller than most wavelengths of light. Okay, because it's a small object, I can do a lot of stuff, can't I? But if I try to measure the distance between me and the moon, all of a sudden my parameters have changed, haven't they? The techniques I can use are totally different. Okay, new ones open, but a lot of ones close. And my limits of my accuracy go down tremendously. Okay, so one of the things that you need to understand is that analytical chemistry is one of those fields where you really are having people's lives in your hand. Okay, let's say an analytical chemist messes up. Okay, the drug is supposed to have the amount of toxin, that would kill 1 in a million people. Whoops, the analytical chemists, it's now up to 1 in 10,000 people. How much of a difference did that make? I mean, it's still 1 in 10,000. It's still pretty good, isn't it? What if it's the vaccine for COVID? Was that still good? No, that was given to 2 billion people, right? You have killed probably millions, haven't you? When you're all said and done, long-term effects. I mean, you've changed millions of people's lives, right? Whoops. Okay. By the way, that was like a super real example right there. Does anybody know how many, what they tested the vaccine for COVID on? No. Do you know why you don't know? Huh? They didn't release it, yeah. They fought releasing it in court and slow released it over the course of 10 years now. So we're about halfway done. They tested it on 10 mice. A vaccine they were going to roll out and use on billions of people, they tested on 10 mice, right? Wow, right? Now, did they have good reasons for doing that? Of course. Doing a larger test would have taken more time, and they were panicking because they didn't know how bad this was going to be, right? But like, this stuff really matters, okay? Of any chemistry, of any science, really, this stuff probably has the single largest impact of any science, period. Okay? So it's hard to come up with a one that has larger impacts for when people mess up, right? And that's why whenever you see an analytical chemist and they're supposed to give you opinion on something, they triple, quadruple check it, even if it's something really minor, because that's just how an analytical chemist should be. Okay. All right. So the WHO estimates that substandard, less drug than expected, and falsified antibiotics are actually a global problem. For low and middle income countries, 1 in 10 medical products are substandard. For high income countries, about 1% of prescriptions from brick and mortar pharmacies are actually substandard. Keep in mind that we're talking about 300 something million people getting these things, right? So 1% sounds low, but is not actually that low, is it? Okay? You're talking about millions of people every year, aren't you? Yeah. Up to 50% from online pharmacies are substandard. This actually mostly has to do with delivery systems and monitoring up to delivery. For example, packaging, right? There's a very short window when you pick it up from brick and mortar for it to be in the sun and hot. When it gets delivered to your door, there's a lot bigger of a window, isn't there? And so your amount of substandard drugs shoots up tremendously. 72,000 to 169,000 children die each year because of substandard and falsified antibiotics. It's a worldwide figure. For the population of the planet, that actually is not that large. It's actually one of the lower numbers that it's ever been, though it has been lower at times in history. So saying that number is higher or low is a bit of a hard to say. Pills, bottle, packaging of substandard drugs can be indistinguishable from authentic drugs. Really, you're probably not going to know if the drug is substandard. The only one I would say that I'd comfortably know most of the time is aspirin, because how it degrades is it goes to acetic acid vinegar. So it starts smelling like vinegar. But very few of them would you ever be able to figure that out. Okay. Only chemical analysis can determine whether the tablet contains the right quantity of drug, and there just simply is no way that pharmacy is going to sit there and do every single tablet they're going to give you, right? And there's no way you're doing that every time you get a tablet, are you? And so you got to gamble your life that the entire chain did its job. So let's talk about a quantitative chemical analysis versus qualitative chemical analysis. Everybody that's taken organic chemistry knows qualitative chemical analysis really well, okay? Because we use it all the time, and we're fairly, we don't use quantitative very much, okay? So this is going to be quantitative, a measure of how much of a chemical substance is present. So that would be like I have a 99.54% of this chemical in this. And then my impurities are this, 1 part per billion of this one, 1 part per million of this one, etc. Okay? And that would be quantitative. You have actual numbers and percentages and amounts. Okay? The analysis provides a numeric answer typically. And a great example of this, that's an industrial example, is does this mineral contain enough copper to be an economical source of copper? In which case you want a certain percentage of it to contain that. Because if you have to process too big of batches with too low of amount of copper, it's not worth it. Okay. Really interesting side effect that just got published, by the way, is there's kind of some central locations we put the slag excess materials from when we do mineral extractions. Because those are fairly centralized and we built those up over years, those locations have now become new mining locations because they've artificially increased the percent of those other stuff, right? So it's actually kind of a fascinating thing. Yeah. So qualitative chemical analysis, the identification of what chemical constitutes are present in a substance. You'll probably really recognize that from the other chemistries, right? What is that thing? Okay. What did we make? What did we extract? What is the identity? Okay. One of the examples of this is, of course, is the patient pregnant? Yes or no, right? It's a quality of it. The test is going to confirm identities of that compound. In this case, the patient pregnant, it's actually the presence of a hormone. Okay. This is actually why you can get false positives for pregnancy tests, is because it's a hormone. If that hormone goes up for other reasons, you can detect pregnancy, right? Yeah. And so you do have to really watch out. Let's talk a little bit about device for detecting falsified pharmaceuticals. So analytical chemistry students are going to be enlisted to analyze medicine collected in low and middle income countries oftentimes. A paper analytical device is used for detecting falsified pharmaceuticals. Each of the 12 lanes on this is going to contain reagents that will react with specific samples. Powdered sample will be widely spread, wiped across the lanes. And then the bottom of the device will be placed in water. And that's what you're seeing there in those diagrams. And the water will actually wick up the lanes. It'll dissolve the reagents, initiating reactions among the different lanes. Okay. Depending on which lane lights up, that lets you know what chemical functional groups are in it, and thus what chemical you have mostly. Okay. They have a reasonable specificity for the cost. Okay. These are extremely useful for what we would consider third world or developing countries. Neither of those terms are actually very accurate, but because these can cost as little as like 50 cents a pop to make. Okay. And so you can test a batch. Usually if your batch is one pill in the batch is right, then they're all right. Okay. People don't normally trade out just a couple pills. It's usually the whole batch. Does anybody know that how common this is, by the way, for people to trade out drugs in these developing countries? Mexico had over 1 million batches that somebody traded out the drug for a white random white powders they happen to have in their house. That was only 5 years ago. So this is not uncommon at all, and is incredibly necessary. And you would be shocked about what people will do for this, like how willing they are to put. One of the batches that they traded out had lye, just straight up poisons they put in. And one of those batches actually got missed and ended up in the United States. And it was a big thing because they poisoned their baby. Yeah. But anyways, that's digressing. All sorts of stuff there. So let's select a method. Criminals may add just enough drug to falsify tablets to fool a qualitative test, but not enough to cure the patient. And so if they're like at a little smarter long-term strategy that they want to try to do this for like a decade, what they'll do is they'll half the amount that they're putting in. And so everybody's doses are half off, right? And then you're doing your body weight. Your doctor is taking your body weight and figuring out your dosage. Well, they're always going to be half off. Okay. And that way the person making the pill can resell those, usually for about a fifth of the cost of the actual drug. And they can make some pretty decent money for one of these countries, right? Honestly. They can become pretty rich for one of these countries. So, has anybody ever heard what crime will a capitalist not commit for $100,000? It's a Marxist quote. No? And you've probably never heard the rejoinder to it either, have you? What crime will a communist not commit for a steak? Nobody knows the history of communism, do you? Oh, that's sad. So if you ever watch movies about like Russian mafia, they're always a butcher. And the reason is butchers in the Soviet Union were incredibly powerful because they could cheat and have extra steaks outside of the communist proportions that you'd be allowed. And so they were very, very wealthy and wielded high power positions just because they were butchers. And they would often be very corrupt and end up as like bosses of local mafias and stuff. Yeah. So anyways, people, no matter what system, are going to be corrupt. They're going to be willing to hurt people for money. And really the only difference between any of the systems is how much it costs for them to be willing to hurt people for money. So in a capitalist system, it typically tends to be in the 100,000 range because they're just not willing to do stuff like that for $10,000. 10,000 just isn't worth that much to them. But in some systems, that price goes down a lot. Okay. So how does analytical chemists measure the amount of pharmaceutical in a sample and ensure that the answer is correct? Well, This is actually an incredibly long answer, which is basically the rest of the course, right? But one of the ways you start this process is you start by searching research literature. Hey, guess what all of you in research are going to be doing? Start with research literature, right? And this is why journals can charge a lot of money, is because corporations have to buy them to figure out how can I test this specific compound or drug or whatever. Yeah. Yeah, you've probably seen some of that. Yeah, they're willing to put a lot of money into it to find the answer, right? No. It costs them more for each person.
Yeah.
Actually, it costs only by terminal. So technically, it doesn't cost them more. Yeah, no. They probably want to keep the terminal open. So it was found that pharmaceutical industry uses HPLC to quantify drugs, and that the standard methods are available for most commercial pharmaceuticals, including ciprofloxacin. And so HPLC is kind of like the gold standard nowadays. Realistically speaking, most drugs are actually detected their identity qualitatively, HPLC. And even if they want to do quantitatively, HPLC is still a very good method. Okay. So sampling is the next thing you have to figure out and determine. So the first step in any actual chemical analysis is going to be procuring representative samples to measure. The process would be called sampling. And this, everybody thinks this is easy when they aren't actually scientists and not actually doing analytical, like the people that don't actually make the methods. But in reality, this is actually probably one of the hardest parts. This is the one that the person designing the method usually screws up. Okay? And I've seen dozens of large companies mess this up and get false positives everywhere because they mess sampling up. Not because of everything else. They have a $500,000 HPLC. It's the best thing they could get. Their SOPs for that are well figured out because they looked them up in journals, got them from the company, but they didn't get a sampling method from the company, right? Because the company has no idea what you want to do with it. Okay? And then they don't hire somebody like me. They just have like random person that has never done anything but run the machine. And their sampling is messed up. They have lead blood samples that they're leaving in shipping yards for 2 weeks. And now they're so degraded they can't actually get a positive out of anything anyways. Okay. So, for example, here we see an undergraduate, Sarah Blees, Dr. Maria Lieberman, collaborating with a pharmacist, Dr. Mercy Main, and a pharmaceutical coordinator, Felix Ware. They're obtaining pharmaceutical samples in Kenya. Why is there such a big team? I mean, the undergraduate's probably the one that's going to run all the samples. Yeah, they need to obtain the samples, don't they? And, well, aren't that just going to be the pharmacy people? They're going to obtain the samples? Why do the other people need to be there? Yeah, they're reviewing the sampling technique, aren't they? Okay. And so they're developing a sampling technique for the pharmacist to follow, sending it to her. She follows the second part of the sampling technique so they don't sit it under the heater or light or whatever for 2 weeks. They have somewhere they put it that's controlled. And then they actually do the actual analysis. Okay. Let's talk about heterogeneous versus homogeneous. So, or heterogeneous versus homogeneous, depending on which side of the Atlantic you're on. Heterogeneous is material composition that differs from region to region, of course. This sample may contain multiple active ingredients pressed together to create non-uniform tablets. Has everybody seen their vitamins? And they have like little speckles in them? Yeah, those are heterogeneous, right? If you tried to sample one of those and only took one sample, didn't get it homogeneous, you'd get very different answers depending on where you went, right? Homogeneous. Material composition is the same everywhere. You can obtain this by grinding tablets into fine powder and then mixing them very carefully. You can also obtain it by dissolving them, right? Depends on your next step of your technique on which one's a good answer. So let's talk a bit about sample preparation. One of the more common ways of sample preparation is going to be mortar and pestle. This is how you grind a powder down so it can be nice and uniform. You mix it up. Please note that if you do a sample of mortar pestle properly, you'll actually mix while you're doing it. Okay? How you actually do it is you press up against the side and then rotate your mortar as you go along. Okay? Okay. It isn't this. Just how everybody always wants to try doing it. So, focusing on that antibiotic, tablets may contain multiple active pharmaceutical ingredients. Rarely is the entire tablet the active ingredient. There's typically either multiple active ingredients or there's something to fill it in. Okay? Because drugs are typically too small concentrations to just measure directly out. It may have inactive excipients. This is the other stuff that fills in. Typically, this is things like lactose, starch, cellulose, very, very commonly cellulose, which is wood pulp. Which, yes, they're feeding you wood pulp. Falsified tablets may also contain unexpected materials. These could be things like heavy metals, talc, chalk. Sometimes people that are falsifying these tablets just don't care or don't know, right? And so it can be a pretty wide variety of things. Before analysis, each tablet is going to be weighed and ground to a fine powder using a mortar and pestle. And then you'll try to get it as uniform as possible. So then you can take usually multiple samples from that and test those. Okay. So substance that is measured. In this case, this is going to be called an analyte. That's the thing you're looking for. That's what you're measuring. Okay? You're analyzing it. So it is called the... Everybody with me? Analyte. Thank you. Get used to saying that. Analyte. Dr. Clausen, I did not discover the analyte in that sample. Okay. The quantity of that analyte to be measured, i.e. the mass of the ciprofloxacin per tablet, is going to be called the measurand. Okay. So, measurand. The next step in sample preparation in the procedure is to make a quantitative transfer. What do you think a quantitative transfer is? You've done a lot of transfers, right? In all sorts of chemistry labs. But usually those are qualitative, right? We're really just concentrating on getting it over to the other deal. If we lose a little, whatever, right? We don't care. But in a quantitative transfer, you need to know exactly how much you got over. Okay? And in the organic chemistry course, we do a quantitative transfer over the 2 semesters. But it's pretty rare to do. So it's going to be a transfer of that sample from one container to another to make sure that none is lost. The residue is not transferred into the flask, has to be a result in the final analysis error. So for the powdered ciprofloxacin, we'll use a crease weighing paper. That's going to help to funnel the powder to a volumetric flask because we're going to dissolve it eventually. We'll carefully then rinse the funnel using acidic phosphate buffer. And what that will do is it'll put more of it down in there, right? Knock it down in. And I'll give the improved solubility. That's why it's acidic phosphate buffer instead of basic, etc. Okay. When fully dissolved, you'll dilute to the volume in the volumetric flask and mix thoroughly. And then what that will do is it'll give you a more manageable concentration. Okay? I.e., think of it this way, right? If you were to measure the weight of a hair, how successful would you be? Not, right? Almost impossible. But if you increase that weight up to something that's not going to blow around everywhere, let's say a penny, you're going to be very successful at measuring that weight, aren't you? Okay. And that's why you do things like diluting these. you know your dilution because you can do it through math, right? I diluted this amount into this amount. And what that'll do is all your subsequent measurements are now much easier to make. You can make those much more accurately because they're going to be larger amounts, more within the range of your instruments. So you may have to filter sample solutions to remove any remaining solid particles. This is very common because, for example, talc powder is not going to dissolve in your buffer. So only after all of this procedure is that state of that tablet suitable for analysis. You've now made something you can actually analyze. Okay. This right here is actually one method to do a filtration. This is a syringe filter. This is a small batch method. Okay. You could just outright gravity filter, right? If it's a large enough batch, it's the right size. Okay, now we can do a chemical analysis. My goodness, that took a while, didn't it? Okay, and this is why everybody gets stuck on the chemical analysis part of this. But in reality, the other part is usually just as long or longer amount of time and just as important. Okay. Chromatography is going to separate the components of the sample and measure the quantity of the analyte. And so we'll be using chromatography in this case. A column is going to be packed with silica beads, usually, SO2. Ciprofloxacin is going to have a greater affinity for the hydrocarbons on the silica surface than it does for the mobile phase or the solution. Okay. So the ciprofloxacin is actually going to stick to those SO2 particles. That's what you're seeing right here. And it's going to slowly exit from the column, whereas the other components are going to move much faster. The excipients, which are the non-medical components, are going to pass through the column fast, and they'll reach the detector first before the what you're looking for, the analyte. Okay, and that's what you're seeing right here. It's sticking. It's going very slow. The other stuff goes faster, and that's what you're seeing these bands. See how they separate out? Okay, and so your excipients hit the detector first, and those are going to come off as little peaks. And those are the excipients. And then this one, which is ciprofloxacin, the analyte is going to hit the detector, and that'll come off as a peak, and that will be your active ingredient. Okay. And then what you can do is, if you have the right detector here, you can actually measure how much came off. Okay. So analytes are going to be detected at the outlet because of their ability to absorb ultraviolet radiation from your lamp in this case. This is a very simple UV detector chromatography. This would be, did you all use UV instruments in general chemistry? Use it for Beer's Law? No. Okay. We'll use some a little bit here. More next semester, we'll go into more detail on UV instruments and instrumental. But essentially, it's how well you absorb UV radiation. So this graph right here actually detects your response versus time. This is a chromatogram right here. You can always tell the difference because it's versus time, how long it took to come off. Okay. This right here is actually the major peak in the chromatogram right there. The chromatogram alone does not inform what compounds are present actually. One way to identify peaks is to measure the spectral characteristics of each one as it emerges from the column. For example, in this case, what we have is we have a light source that's absorbed very well by ciprofloxacin. And so that's one of the pieces of evidence is the ciprofloxacin. Okay? Is that our light source in this case, that frequency we're using, is absorbed very well by that. Okay? And that's why you don't see the other stuff very much, like the excipients here. There's a fair amount of that stuff, but it just doesn't absorb in that wavelength. Another way is going to be an authentic analyte sample to the unknown, see whether the analyte peak grows. So what you do is you actually just straight up add ciprofloxacin to your sample and see if this peak gets bigger. If it gets bigger, then it's ciprofloxacin, right? If you see another peak show up, whoops, not that. Okay. Oh my goodness. I'm gonna just go over every time, aren't I? No, this is actually the lecture. So analytical chemistry is the one